Good afternoon to all of you, and welcome to this live interaction session for advances in welding and joining technologies. I hope you have already gone through the few modules, like for example, fundamentals of welding and joining processes, and then we discuss about the laser and electron beam welding process, and after that there was the discussion related to the solid state welding process. So all these different welding processes, conventional processes, as well as the advancement in this particular direction, we have tried to explain in our video lecture, in my video lecture. So definitely you have gone through some assignment problem also and some theoretical analysis associated with this course, but this live interaction is mainly meant for suppose if you have any doubt or maybe there is some difficulty of understanding during that when you're trying to follow these video lectures, maybe we can discuss all these aspects at this moment. So I think there is not much of coverage done so far, but up to that point, we have solved some assignment problem or you have gone through all the theoretical aspects associated with these particular courses. Maybe you can ask or you can raise your hand to discuss some particular points. But before that, some general questions normally arise, or maybe from the most of the cases from the student's perspective, that we'll try to discuss first, or I will try to give you some kind of the overall view of this particular course first. Then we'll discuss, we'll interact with respect to each other, and I'll try to answer your questions, whatever you're having any doubts related to this particular course. Actually, once when we share that our Excel sheet to ask some queries beforehand also, I didn't find any questions there also. But anyway, you can ask directly these questions now itself. But before that, if you look this structure of the course, that I mentioned the several reference book also. So apart from the video lectures, if you go to the reference book, some sort of clarification may be done, or understanding or advanced studies will help you to resolve certain problems associated with the welding and joining processes. For example, this reference book, I mentioned this thing that different area, actually the physics of welding, one particular area. What are the principles of welding that there you can follow the reference number 1 and 2. That is sufficient to understand the physics of the welding process. Then, if you are very much interested to the very small scale joining processes, then you must go through this particular textbook, that micro joining and nano joining. This is a very good book where you can find out the different issues associated with the very small scale welding process of medical devices or any other kind of micro joining, or even for the nano joining processes. Apart from this thing, if you are interested to understand the laser, specifically the laser welding processes, then this is the fourth book, is the very good, interesting book associated with the laser material processing or maybe laser welding processes. If you are towards the understanding that the metallurgical aspect of the welding process or welding metallurgy problem, the reference book 5 is the very basic books, or very at the same time very resourceful book associated with the welding metallurgy. And this book is very presented also in very simple way to understand all the topics related to the welding processes. Then, if you are more interested to look into the different computational aspect, if you want to develop some model or try to calculate the temperature distribution during the welding process, then book number 6 is the most interesting book. And apart from this thing, suppose you are very much nowadays there is a tremendous use of the solid state welding process, specifically the friction stir welding process. Then book number 7 is you get the lot of information associated with the friction stir welding process in the reference number 7. Apart from this thing, you want to know advanced welding processes, and that is the book number 8, or reference book number 8 is more interesting. The development of the welding processes. Apart from this thing, that book number 9, if you are computational welding mechanics, here also you can find out the computational welding mechanics, but specifically if you want to develop some finite element based model or numerical model and heat transfer analysis, the stress analysis, then this book is more appropriate to understand specifically the reference number 9. Even for also modeling aspect, not only for just to develop the model. Apart from this thing, some interested, relevant, there's a problem can be associated also in this particular book. Apart from this thing, if you are trying to develop something or try to understanding some additive manufacturing process, then this is a very basic or textbook, the reference number 10. So overall, we can see that there are so many reference books, and we can see that there are different area coverage of the area is there associated to the different references. And definitely, if you want to understand the process, not only the overall view will be getting from this particular video lecture process, these video lectures, but if you try to focus on one particular direction in welding process, then you can see all these textbooks I already referred. And in depth on understanding in depth studies, if you are interested, then you go through the individual reference books. Now, over the few years of understanding or experience to run this particular course, I come to know that this is a very common question normally arise, or maybe people ask, or the students who are attending this course, they ask this particular few questions I just mentioned here. One question is that what will be the pattern of the exam? What will be multiple type questions or only pen paper exam? So here, this particular course is mainly associated with all the multiple choice type questions. So you'll be getting the 4 options, and out of the 4 options, you have to choose the correct one. So this similar pattern also we follow in case of the assignment. So what pattern you can get in the assignment, the similar kind of the pattern you can expect in this final exam paper. So that is the first question. Second thing is that technical question has been asked that about the nature of the metallurgical aspect of the slag that will be better. Different slags play the different role on weld quality. Definitely, slags is having that different role also. They not only the protect this molten oil pool in specifically the fusion welding process. It is also having the role to maintain the quality. That means quality means basically you are trying to expect that to avoid any kind of the defects. So to avoid any kind of the defects, definitely slags also having role in this case. Not only slag, also that different tests of the shielding gas also having some role to maintain the quality of the welding process. But it's a based on the experience basically, or some sort of the kind of empirical relation may exist to understand the oil quality and how it is related to the different slag formation in particular process. Third is that laser welding is which type of process. Sometimes people may confuse that we are using because there is a wide application of the laser. Everywhere you can find out the application of the laser in each and every sectors. But laser welding, when we are talking about, is what type of the process. Normal laser welding, we normally understand the fusion welding process because it melts the material, and then subsequently then maybe the solidification occurs and join the 2 components. So in that case, the laser welding means that it's a fusion welding process. But in other way also, sometimes you use the laser source for other hybrid welding processes. So even for the solid state welding process, just to heat the sample, but not the melting purpose. But that is in that case, laser is not the main source of the heat generation during the welding process. Rather, laser can assist to develop the different welding processes. So therefore, normal laser welding means is a simple way we understand that it's a fusion welding process. Now next questions, if 2 materials with the different densities are welded, how will be the weld heat formula gets changed? Definitely it's a very good question that when 2 different materials means 2 different materials, they are having not only density differences, their thermal conductivity and other physical properties are completely different. So in this type of joining of the materials we normally call as the dissimilar welding process. So in the dissimilar welding process, since diffusion zone will be completely different if there is a huge difference in the properties. So therefore, you can expect the one side the fusion zone size will be much bigger as compared to the other side of the other material. So in that case, we can utilize in the more effective way that specifically numerical modeling approach. We can use the double ellipsoidal heat source model, but normally for similar type of the material, but dissimilar type of the material, we can use the quadruple heat source model. Quadruple ellipsoidal heat source model. That means you can divide the zone into 2 different part of the ellipse, that size, major axis and minor axis, maybe you can adjust depending upon the type of the material. So that's why quadruple ellipsoidal heat source model is the most suitable when you two dissimilar materials joinings are normally done. Third is that what will happen when we use the AC current for welding process. Definitely most of the case you can find out the welding of the steel. We normally use the DC current, and there is a different current voltage we set it in a particular machine, and then we try to perform the welding process. Now I'm talking about the fusion welding process. But if you want to join the aluminium, so aluminium there is a high tendency to form the aluminium oxide on the surface. Very quickly, aluminium oxide can form on the surface. So every time there is a need to remove this aluminium oxide, it will be harder as compared to the aluminium. You know that aluminium is basically relatively softer as compared to the steel, but there is a coating of the aluminium oxide on the top layer. But when you try to join these two components, then it's remove this particular aluminium oxide from the surface. So for that purposes, we use the AC current. The one part it will try to helps to cleaning action of the top surface. So that's why specifically for the joining of the aluminum, we can use the AC current in the process. But I'm talking about the fusion welding process. Next few queries may ask that what kind of the software is used for the simulation of the welding process, because in some point of discussion we discuss about the simulation of the welding process. So therefore, are these software used frequently in the fabrication of division of the industry, or welds mostly modeled through the FEM? Actually, it depends. There is a need, but see, modeling of the welding process is it's a computational method. What way we can develop? We can use any mathematical tool. For example, if you try to develop some numerical model of the welding process, we can use the finite element method. We can use the finite volume method. We can use the finite difference method. And for different methods, we can find out the lots of software also available. So therefore, we normally use the abacus can be utilized in case of the, if you try to finite element method, even COMSOL can be used. ANSYS can be used also. These are the different commercial softwares available in the market. You can utilize any kind of the software, but not only necessary that you can analyze the heat transfer analysis or stress analysis can be done only through the FEM method, finite element method, but other finite difference, finite volume method can also be utilized to develop the model. There is another question that polarity in terms of details means that more heat is generated in the electrode and when in workpiece. So basically polarity means when you try to look into the any kind of the fusion welding process, you make an electrical circuit on this thing, and there is a power supply. Welding machines can attach with the power supply, and then normally use the voltage is lower side and the current is very high. That is the usual procedure for the fusion welding process. Now polarity means they're creating the arc. When it is complete when there is a creation of the arc, that means complete the circuits. So it is connected to positive terminal one sided and negative terminal on the other side. Now there is a possibility of the electrode positive and the workpiece as a negative terminal. If suppose you connected the workpiece as a positive terminal and electrode as a negative terminal, then the electron cloud between these two positive, and it will always try to flow towards the positive side. Positive side means, for example, electrode is workpiece is positive sides, then electron will try to follow the flow towards the positive side. So therefore heat generation will be much more in the workpiece and heat generation will be less in towards the electrode side. So that's why depending upon that, you can use the direct current electrode positive, direct current electrode negative, different kind of polarity can be utilized. For example, say gas tunnels are welding process. So in that case, your intention is not to melt the electrode. So therefore you try to keep the electrode should be the minimum heat generation and workpiece should be the maximum heat generation. So therefore you connect the workpiece with the positive terminal, electrode with the negative terminal. Then you can get the maximum heat generation. Around 2/3 of the heat generation can be expected on the workpiece and 1/3 heat generation will be the electrode. This is one means. Suppose if you are using some consumable electrode, for example, gas metal arc welding process, you want to consume the electrode more. So therefore, through the electrode sides, the heat generation should be much more and workpiece would be less in that case. So therefore, the electrode will be the positive terminal and workpiece will be the negative terminal can be associated with that. So that's why depending upon the application, we can utilize the positive terminal and negative terminal in a welding process. Last question, that can material of fixture will deflect the beam even metal A and B? I think it is associated with some sort of the electron beam welding process. We'll discuss that part. Before that, few things I just like to mention, and the few that whatever chapter has been covered so far, two significant part I'm trying to mention in this particular live interaction. One is the physics of arc welding process. So physics of arc welding process, we understand that the voltage and current is required. So voltage means the potential difference that causes the current to flow, and current is the movement of the charged particles in particular direction. So now potential difference, but in welding process, potential difference is very requirement is low, but current flow is much more. And polarity means which part we are connected to the workpiece terminal and which part we are connected to the electrode terminal. So accordingly, we can decide the polarity. That means direct current, electrode, DC current we can utilize, electrode negative, and direct current, electrode positive. That is the two polarity DCEN and DCEP. Apart from this thing, sometimes we can utilize the AC current. I already mentioned that in case of the aluminum, we can utilize the AC current. Now, heat generation in the electrode, depending upon the GTAW and GMAW are different, because heat generation in electrode try to be minimized in case of the GTAW process, but try to maximize in case of the GMAW process. So in that case, the polarity can be different. Even for the DC current, the polarity will be different in case of the GTAW and in case of the GMAW. Just I explain all this matter. Now, electrical circuit, the electricity flow from the power source, that is the, we can see any welding machines there. And it's a passage when you're creating the arc through the electrode, and across the arc is the flow of the current. Now, basically in welding process, when you're creating the arc, it basically converted the electrical energy into the thermal energy. So thermal energy, the heat generation will be there, and then this heat will try to melt the material because of the heat generation, and then after that, when you're joining the material in the liquid phase, and then gradually solidify. After solidification, we get the solid joint between the two components. So this is the basic process associated with the any kind of the fusion welding. Sometimes you face the difficulty understanding the enthalpy of melting, because when you're creating the arc is interacting with the substrate material. Then when it is interacting with the substrate material, then it will melt certain part that creates the fusion zone, molten zone, and the heat affected zone. But how to estimate what is the amount of the heat required to define particular volume or to define the oil pool. So heat required to melt the oil pool volume is basically heat required to melt the solid. Solid means we basic calculation we try to first is reach the melting point temperature, and at melting point temperature there may be the phase change. Phase change means from solid to liquid phase. So therefore, both component of the heat has to be added. One is the specific specific heat associated to raise the temperature up to the melting point, plus L means the latent heat of fusion. But be careful with the unit of this thing, at which unit the latent heat is also given. So first part is the raise the temperature up to the melting point, and second from room temperature, and second part is the add it to the latent heat of fusion to account the change of phase from solid phase to liquid phase. And even if you have the data or information available, if there is some superheat also, then superheat can be, we can count. But in that case, we need to know what is the peak temperature, this thing. So therefore, in that case, at specificity of the liquid, then you'll be able to find out what is the superheat required in this part to generate the oil pool volume. So therefore, there are three components of the heat you can calculate. One is the because of the change of the specific heat, because of the specific heat content in the solid phase, plus change of phase liquid to solid phase, the latent heat has to be accounted, plus if there is any superheat, then superheat has to be accounted, and that consider the total enthalpy associated with the in a welding process. But if I ask you what is the total enthalpy of melting just to reach up to the melt point, then two components will be there. Specific heat due to, and another is the latent heat. These two parts will be there. Now, sometimes we confuse the surface active elements. Surface active elements actually, if we already have explained, but if we try to look into this thing in fusion rolling process, along with the material, if there is a presence of the surface active elements with the molten pool, it actually modify the flow pattern, the molten material flow pattern. So that directly impact on the fluid flow pattern. So that actually dominant driving forces for the fluid flow. And in that cases, we consider the surface tension force, and this surface tension force actually change depending upon the presence of the surface active elements. Here you can see that thing, surface tension, how it is changing, the surface tension force changing upward direction, and you say the negative slope and the positive slope. In these two cases, the pattern of the oil pool are completely different. One is the flat pattern, the width is much more and depth is less, and other cases the width is less but depth is much more. So this, the surface active elements actually change the surface tension force, and once there is a change in the surface tension force, impact on the flow pattern within the small oil pool, and flow pattern decides the what is the particular schematic shape of a oil pool. Here you can see that at one example you can see that 180 to 600 ppm oxygen in SS304, it actually produces the maximum oil penetration. That means in that case, between 180 to 600 ppm oxygen in SS304 acts as a surface active elements, and it try to produce the when presence of the surface active elements try to maximize the depth of penetration and minimize the width. So that we can take as an advantage the presence of the surface active elements to can achieve the full depth of penetration in case of the oiling process, even for the gas transfer alcoholing process. Yeah, just to explain the different how it is acting. For example, first case is the pure iron. Pure iron, there is no presence, there is no surface active elements. The flow pattern is normally from center point to outward periphery, and surface tension is acting from center to outward periphery. So in that case, if this is the flow pattern, you can observe that width is much more and depth is less. But in certain case, the iron and sulfur, very small quantity of the presence of the sulfur in a steel also. In that case, sulfur acts as a surface active elements, and here the flow pattern is completely reversed because of the surface active elements. Now, in that case, we can see that it is the from anti-clockwise direction, the material flow pattern, and this surface tension force acting towards the center from outward periphery to towards the center. So that actually try to enhance the depth of penetration and try to reduce the width. So when you try to enhance the depth of penetration, then we can achieve try to achieve the full depth of penetration. That is advantageous to get a good oil joint. So to achieve this high depth of penetration. Even that is the significance of the surface active element. So we can that there are three different ways we can introduce the surface active elements. For example, the surface chemical composition of the base material. It means that surface some quantity of the surface active elements is already existing in the base material. Second option is that the spreading the fluxes. So say oxides on the substrate material, simply spreading the oxides on the substrate material, that actually say titanium oxide or other kind of the oxide we can spread over the surface, and that acts as a surface active elements when you try to do the oiling process. Or other way, you can make the active gaseous addition. For example, CO2 can be added with the sealing gas, and in that case, here the oxygen can act as a surface active element. So there are different ways to introduce the surface active elements during the oiling process. So based on the concept of the effect of the surface active elements, then industrially activated TIG welding process actually has been developed. It is some modification of the simply TIG welding process, tungsten inert gas welding process or GTAW process, gas tungsten alcoholing process. So that is modified. Presence of the taking the concept of the surface active elements, this TIG process has been modified, and then industrially activated TIG welding process actually has been developed. Other part that sometimes we can see the electron beam welding process of dissimilar material. This is actually very common problem when you try to join the two different materials having the different properties also, as basically the magnetic properties are different. In that case, we can face the difficulties using the electron beam, because in electron beam welding process, we normally join the two components that very high thickness of material, which is not possible to join using conventional arc welding process, or even there is a limitation of the laser welding process. In that case, we try to join the two components in the using the electron beam welding process. So this electron beam welding process, we can reach very high depth of penetration for the material. So that's a very high thickness of material. We can use the electron beam welding process, and if material is the very costly material, in that case we can, because electron beam we understand the electron beam occurs in a vacuum. So in that environment, that we can join these two components. But what happens when you two materials are different? So then residual magnetism actually creates, and even there is a presence of the fixtures also. That in that case, the thermoelectric magnetic field will try to deflect the electron beam towards the one type of the material. So that is because of the Seebeck effect. So because of the Seebeck effect, that the deflection of the beam can happen towards the one particular material. So that is the usual problem in case of the dissimilar welding of the electron beam welding process. Now, these are the, we can find out these difficulties, the combination of these two materials, the iron and copper, stainless steel and low carbon steel, even for the low carbon steel and the nickel copper alloy. So this combination of the material, we can find out this thing. Because the Seebeck effect, according to Seebeck, some electromagnetic force is actually generated due to the temperature gradient of the two different materials. So there, here you can see the Seebeck EMF, the electromotive force, can be calculated minus S into delta T. Here the S is the Seebeck coefficient and delta T is the temperature gradient. So that actually introduce this EMF, generated EMF, try to deflect the beam one particular direction. But if there is a both are the same material, though we cannot face this kind of the difficulties, these kind of the problems associated with the electron beam process. I think this is not required false characteristic. Now we try to compare between the laser and electron beam welding process. If you see, mostly you can see that the electron beam welding process very narrow or very narrow weld zone and heat effect zone you can expect, and even laser also, but it's not as compared to the electron beam welding process. Deep penetration can achieve in the electron beam welding process. Even laser welding process, you can achieve the deep penetration, but I have written the lag penetration because as compared to the electron beam, this penetration depth can be less in case of the laser welding process. Welding speed becomes very high speed you can utilize in case of electron beam welding process, but laser welding also, it is also very high as compared to the arc welding process, but it should be less than of the electron beam welding process. Shielding gas, electron beam welding occurs under the vacuum, so there is no question of the contamination of the welded zone. So in that case, there's no requirement of any kind of the shielding gas, but laser welding process we can utilize there are different shielding gas. Vacuum chamber electron beam welding process is required, but laser it is not required. But cost is very high in case of the electron beam welding unit as compared to the laser. Generation of the X-ray is possible in electron beam welding process, but that is not possible in case of the laser welding process. But power efficiency for electron beam is very high, 80 to 90%. But laser welding, because electron beam welding occurs under the vacuum, so therefore we can expect the almost all utilization of the power. But laser welding, we can that reflection of the light on other issues, that we can expect the efficiency, power efficiency is very low in case of the laser welding process. Even power efficiency is very low in laser welding process, even as compared to the arc welding process also. Size of the workpiece is the one of the issue associated with the electron beam process, because size of the workpiece is decided by the vacuum chamber in case of the electron beam welding process. But laser welding process is not limited. So these are the very specific differences between the electron and laser beam welding process. Now I just one slide I have shown with the heat generation associated with the friction stir welding process, how you can calculate the heat generation associated with the friction stir welding process. So here you can see that friction stir welding process, the tool solder tool is there and the tool pin is also there, tool solder also there, and here you can see that there is a frictional heat generation in the contact surface, so solder surface. So here you can see that you can find out the total heat, due to the sliding friction and sticking friction. We can divide into these two parts, and we can find out the elemental, the heat generation for the elemental area dqf and this thing. But you can define the relative motion between the workpiece, between the tool and the workpiece. There you can see define the contact state variable delta between this ratio, and the delta can be varied from 0 to 1 like that. So accordingly you can decide the sliding or sticking situation. And then we apply the different contact friction law, that one case is when there is a sliding, So Coulomb's friction law, we can apply the contact friction P pressure into the coefficient of friction. But when sticking means the plasticide metal is exactly sticking with the workpiece. So in that cases, you need to overcome the yield stress value. So that's why sigma y by root 3, that is called the shear yield strength value. So it should be in that cases the contact shear stress will be equivalent to the shear yield strength value at the purely sticking condition. Combining these two, we can estimate the total heat generation is the in terms of the solder radius and the pin radius, and this contact state variable and the pressure coefficient of friction and the rotations. Sometimes we can use the diffusion bonding also. This is one of the very old process and in the associated with the diffusion bonding process. So here diffusion bonding means suppose to want components, if you want to join together, then keep in contact these two components, and maybe there may be requirement of the application of the forces, keep it for a long time, then one layer to another layer diffusion will occur. But to occur the diffusion, the surface preparation is very important. So there not be any contaminated layer between when the diffusion to get the successful diffusion bonding. So you have to remove the layer, surface preparation has to be done very in a proper way. Then keep in contact between these two components and hold it with the sufficient pressure for a long time, then diffusion to occur. But it's a time consuming, it takes some time to do this thing. But we can find out this temperature relation between the temperature and diffusion coefficient, something like that. So exponentially, it's varying with respect to the exponentially varying part. And even also time also depends on the diffusion time to diffusion length. So up to which length diffusion occurs, that is the diffusion length can be calculated in terms we can see the dt to the power half. This is a very empirical relation associated with the diffusion bonding process. I think that's all this for the this thing, the presentation. Now we'll try to discuss if we have any query. We'll try to look into all these aspects. Sandeep Chaturvedi. Sandeep Chaturvedi, you have any query, you can type anything. Bhaskar the researcher. So you have any query to but anything related to your assignment submission, all these technical things you can directly mail to this thing, Gmail, or through communicate with the email. Any technical questions you can ask here, I think. Miraj Rai and Dhananjay Chetty. In welding, metal transfer, Lorentz force is a type of retard force. Sir, please explain this. Okay, if you try to look into this, that metal transfer actually, well, if I look into this gas metal welding process, so you try to look at what are the different forces acting on this particular. One is the, so say the consumable electrode is there. So electrode is melting and there is a creation of the droplet from the electrode. So it means that at certain point from the solid electrode to liquid droplet has been created, and that liquid droplet is detaching from the solid electrode. Now, what are the, when detaching the liquid droplet from the solid electrode, there are so many forces acting at this particular point. So one is that surface tension force, there is two different media, one solid liquid. So definitely some sort of the, or even there is a interaction of the shielding gas and the liquid. So in that case, surface tension force will be acting. First thing. Second thing is that arc welding process definitely flow of the current under potential depends. So therefore, you can expect some of the electromagnetic force and Lorentz force. So surface tension force and electromagnetic force. And there is another force because when droplet will be liquid droplet will be created and it is a falling under the gravity also. So gravitational force also there. And some shielding, mainly these three forces, surface tension force, electromagnetic force, and gravitational force. Combining all these three different kind of the forces, it will try to detach the material from this, from the droplet. So this which forces is acting much more. So electromagnetic force or gravitational force should overcome the surface tension force. Then only this drop will be detaching from the electrode. Okay. So that is the way to analyze the different this thing. But what is how the different forces distributed? How electromagnetic force is distributed? It's a until unless we doing now some kind of the simulation, we cannot say that this is the distribution of the electromagnetic force. But if we know it's normally this this in general, we can say that combining of all these three different driving forces is mainly responsible for the detaching of the droplet from the electrode. Okay, and even if you see I'm just taking another example also that gas metal arc welding process you have studied. But have you studied the CMT process, cold metal transfer process? So here what happens? CMT process also, CMT also advanced level of the gas metal arc welding process. So here in gas metal arc welding process, you are not using any kind of the mechanical external aid to detach the molten droplet. So this is the naturally the droplet has been created and droplet has been transferred in gas metal arc welding process in presence of the arc and surface tension for electromagnetic force, gravitational force, all will play and this thing. But you are not mechanically applying any kind of the external forces to detach the droplet in case of the gas metal arc welding process. But in CMT process, what happens? When there is a droplet, the molten droplet has been created and which is already attached with the solid electrode, then molten droplet keep in contact with the workpiece. So that means it creates the short circuit at this point. When there is a creating of the short circuit, means the molten droplet will touch the workpiece material, and when it's touching the workpiece material, then when touching this thing, then this molten droplet will be transferred to the workpiece immediately. So and this happens again when this droplet will be transferred to the workpiece, then there is a creation of the gap between the solid electrode and the workpiece. Then again it will be creating the arc. So this phenomenon is continuously at certain frequency. It is happening. So that's why in that case, the controlled way, this metal can be transferred in case of the CMT process. That's why the CMT process is normally called as the advanced level of the gas metal arc welding process. I hope little bit you understand this thing. What are the role of the different driving process and in case of the metal transfer of the gas metal arc welding process. TKJ thus will find out of all these forces which is predominating. So definitely it depends on this thing. See, a surface tension force is always opposing, basically always opposing the surface tension force, not allowing to detach the droplet. But other forces is acting in the electromagnetic forces and gravitational force. They helps to detach the material droplet from the electrode. But if you just I explain you, if you touch this molten, suppose molten droplet has not been detached from the solid electrode, but once you keep the molten droplet attached with the workpiece, then it will make the easier to creating the short circuit. Then it will be easier to transfer the droplet because in that case electromagnetic force is much more, and that will help to detach the molten droplet to the electrode, molten droplet to the workpiece. So that's why there is a way to transfer the molten material. TKG, is that okay, or you can?
Hello.
Dhananjay, yes.
Hello. Next speak.
Hello.
Hello.
Yes.
Sir, I want to ask regarding metal transfer. What's the pinch force effect on the transfer of in GMW? You tell about the surface tension force, gravity force, and EMF force, electromagnetic force. What is the effect of also pinch force effect on the transfer of the well metal to whirlpool?
Okay.
Do you
So
know
these
about
things.
pinch force?
See, mainly I told you mainly these three forces are acting in this thing. That that gravitational force, surface tension force, and the electromagnetic force. Okay, and even sometimes some role having the say shielding gas, high force shielding gas, also using the high pressure shielding gas, that also try to help to some extent to discharge the droplet, but that is not the main driving force for the droplet detachment. So droplet detachment, the main driving force are the this thing, the surface tension force always try to hold the droplet. So then other driving forces will try to overcome the surface tension force. Then only it is possible to detach the molten droplet from the electrode. Okay, and what are the ways? Because gravitation force definitely it will always be acting towards the downward direction, and electromagnetic force will be certain direction depending upon the flow of the current and all these things. So okay, so it depends electromagnetic force. Okay. So if you change the polarity, I don't know whether there may be the change of the electromagnetic force or nature of the electromagnetic force may be different, but it is also so mainly the when gravitational force is more active. For example, magnitude of the gravitational force is much more as compared to the surface tension and electromagnetic force. Then you can expect that globular type of the metal transfer, big size of the molten pool will occur and it will transfer from this thing. So that means mainly transfer occurs because of the weight of this particular droplet. So that is in that way we can get the globular type of the metal transfer. That means big droplet. Other cases very pink, they're very uh, what is that called? Very small droplets can be created and that can be modulated by the electromagnetic force, nature of the electromagnetic force, or maybe to some extent by the application of the high pressure, the shielding gas flow also influence for the droplet transfer also. So it can be modulated this thing. But depending upon the nature of the mode of the module transfer, then different forces is more with one force is more active as compared to the other, like that. But in general, we can say that surface tension force always try to hold the droplet. So whatever other force is acting, it should overcome the surface tension force, then only able to detach. Now, for this globular kind of the mode or the spray type of the mode, it depends on the what type of the other forces, what way, what is the magnitude of the other forces is acting at this particular point. It depends on that point. Okay, in that case, we cannot say that until and unless this force is more or this force is less, something like that. Okay, so general way you can say like that surface tension force is try to hold it and other forces is try to detach it, and who win accordingly the metal transfer will be occurs. Suppose surface tension is much more as compared to the other two forces, then never metal transfer will not occur in principle, like that.
Okay, sir. Regarding metal transfer mode, I want to ask regarding how the which mode is working in while welding. Suppose short circuiting mode is happening. So how I ensure that the mode is while welding, the mode is it's short circuit mode or globular mode.
See, normally if you try to look in additive, if you want to control the metal transfer, if you want to get a very
How?
smooth appearance of the surface, for example, if you want to expect very good surface appearance of the surface, all these things. Okay, so in that case, short circuit is the better option, because in CMT that only the difference between the GMW and CMT is that in CMT only the control way metal transfer occurs, and that control way try to are developed in the form of a short circuit, basically in CMT process. So there you can achieve very good according to your way that you are, suppose you want to achieve this particular surface appearance, then you have to control the metal transfer. So when you want to control the metal transfer, it is better option to go to the short circuit mode. Okay, but globular type of you don't have, it's a very less control, but a huge amount of the metal transfer is supposedly expected, then you can go for the globular and globular form. But at the same time, globular metal transfer is actually a very slow process as compared to the other metal transfer mode. Okay, so I don't think so. If you say the which is the superior one, I say that short circuit metal transfer is the superior one, because here you can control is in your hand to control the metal transfer in this particular case, and that's why there is a development of CMT occurs. That is obvious as compared to the GMT.
Sir, my question is how I ensure the transfer mode while welding, which is there a
high current? So that is has to be linked with the input parameter. Okay, so current density is very high, for example. Okay, current density is very high. So then droplet, the melting rate will be much more. Oh, that is when melting rate will be much more, metal transfer rate will be much more. Okay, so this particular condition decides, and based on that we can decide the different mode. But this is all subjective kind of these things, relative kind of these things. But there will be qualitative, not, you cannot quantify this thing very typical until I'm doing the experiment. Cannot quantify this. Qualitatively, you can say like that. So very high current. High current is very, then much amount of the metal will be transferred. Current density is very high. So much current density very high means the wire size is small, but you are passing the large amount of the current. Then melting rate will be much amount of the melting will be occur. This thing, and this it will be transferred to this material. So in that case, you can expect the spray type of the transfer. Very quickly, metal is transferring from one point to another on the workpiece. Okay, so that input has to be controlled. So there is a link between the input parameter, and accordingly we can get the output. That means that different types of the mode of the metal transfer. Short circuit. If we simply touch this thing, then it becomes short circuit. Hello,
sir. What I am asking. So we practically cannot decide the parameter range for the transfer mode in GMW process.
But in that definitely, but you have to do the exercise. First, you have to do the trial. Okay, you have to do the trial.
So, sir, I will try do trial, sir. But how I ensure that on what parameter is which transfer mode is occurring? How I ensure?
No, you cannot ensure. Means you have to see that with the high-speed camera, that what are the mode of the metal transfer occurs with the globular and spray. Spray type means very small droplets will be created. And globular means normally the size of the more than that of the electrode diameter. That is the globular. Okay, so that has to be just looking into. You have to ensure that this type of metal transfer with this particular parameter. You have to set it basically. This is the current. This is the value. This is the current. And you increase the current and change the mode of the metal transfer. Then metal transfer, you put the camera and you check it that what are the metal transfer. There is no other way. We cannot say that empirical relation that this is the thing and this is the current and this is the mode of the metal transfer. That we cannot say like that. That's why I told you now. Quantitatively, you cannot say that. Qualitatively, you can say.
Do you recommend any parameter range for this transfer mode?
No, we cannot say like that only unless machine to machine it will vary actually. So it not only that, it depends on the gap between the electrode and workpiece. The arc length also depends. Okay, type of the material, shielding gas flow. Shielding gas also having some role. What is the shielding gas flow rate you are using? What is the nozzle to that? So when you are using the shielding gas, that gap, the nozzle tip to workpiece distance, all parameters are sensitive to the mode of the metal transfer. So it's not like that only few parameters we can control and we can control the mode of the metal transfer. Not like that. You have to set all other parameters as well also. Then only you can say this is that. That's why it depends. The machine to machine vary, and it's a list of it requires lots of experiments to decide the mode of metal transfer and the input parameters accordingly. We cannot say like that. We cannot.
Is the material is affected for transfer mode?
Definitely, material is
Suppose
depending upon surface tension
okay.
force can be different for the different types of the materials.
Okay.
Different material having different melting point temperature also. So surface tension force can be different also.
Okay.
I'm talking about the electrode. Yeah.
Okay. So you do not recommending any parameter range for the transfer mode?
No parameter until unless you are not doing experiments, you cannot say like that.
Okay.
Or maybe if you follow some, for example, you can or maybe you can get this data from the some say AWS standard, American Welding Society standard, and that particular that book, actually code book, there you can get this is the parameter, this is the electrode, this is the electrode type, this is the electrode size, this is the welding current, or this kind of the mode. But normally mode we don't prefer, we cannot say like that, but other we can predict the other way also. Mode is very difficult to predict until unless you are not doing experiments. Yeah.
Okay. I saw some training module of IITG. So in that training, there was a trainer was said that the parameter range of about 150 to 180 current and voltage less than 18 voltage. So for short circuit mode, greater than 180 to 250 current and up to 22 voltage. The globular mode will be
180 to 250. There is a huge range, no? Huge range of the current. 180 to 250. Anything is possible, no? So there is a gap of almost 50, around 70 ampere, no?
Yes.
Oh.
Or greater than 250 ampere or 22 volt. There will be spray type.
What we do, suppose we have a material, even we know the parameter also. But if have the, I have some machines, particular machines, I have some materials, electrode I have, for example, we know the parameter, but till we spend some time on some trials to set first parameter, what is the appropriate parameter to look into this thing, because you have to set the other parameter, sealing gas flow rate and all these things, and all are sensitive parameter. Then only, so we can prescribe certain things, but it's not always be matching with the, we may not get the result within that, but that particular range also. But if it is a huge range, definitely we'll be getting something. But range is huge, no?
Okay. Suppose we are doing some picture and restriction is given by customer is you have to use only short circuit mode for less than 6 mm thickness. So while doing PQR, what will be demonstrating the to ensure the why it's a short circuiting mode? How will we demonstrate while doing PQR?
Well, I'm not getting your question. Can you repeat?
Suppose we have to do one procedure qualification, welding procedure qualification. Okay. And plant has given the requirement for only short circuit mode. Okay. Then while doing PQR, how we demonstrate that is the mode is transfer is a short circuiting mode? How we are going to ensure? Which this is my question.
So short circuit mode, how can you ensure we cannot? You have the instrument of it. Short circuit mode is the simply to show that you show the when set current and all these things and touch the electrode on the workpiece. Okay, and then move the electrode from the workpiece. So metal transfer, whatever melting will occur, that is the short circuit. The simple way we can explain this is the short circuit mode. We have to observe the metal transfer. Sound has to capture the data. Okay. Otherwise, by just simply looking into seeing all these things, it's very difficult to say whether it is globular or spray or what, until unless you not see some camera or whatever.
Do you have any research or any data backup regarding this?
Oh, I think the data generation is a big task actually. So getting the data also a big task. So we have a lot of trials. Then only we get in the actual parameter, optimum parameter. This parameter works well for this particular material, for this combination of these things. Depends.
Okay.
So each and every parameter, if you want to set, you have to do lots of trials.
Okay.
And I told you, no, my data may not be fit with your data also, or sometimes it may not match with the already some specification AWS or IITG, whatever some specification can not always be matching.
Okay. Power source is the same, no, sir?
Power source
All
same.
power sources. So how we
No,
change the
DC to
setting?
DC power source is actually varying because. Okay.
So suppose we are using inverter based power source or CMT process or thyristor. Depends upon power source, the effect of power source on transformer.
Yes, but there's other factors also, the human factors also there. Surface condition also and matter. If you change the surface, which what is, if you are not doing the any surface preparation, then your prescribed parameter may not work.
Okay.
That is also matter.
Okay.
That also matters. So that's why we normally follow that. Anything we are getting, we do our own trial first. Set the parameter first. Sometimes it may happen also. Suppose you have the machines, we are seeing, you can see the display. This is the current and this is the voltage. Okay, so this current and voltage may not be exactly that measurement error, something like this. Some measurement error may be there. That is not exactly reflecting the exact current or exact voltage, may be possible. So even there is a range, within that range also you have to set some optimum parameter for your particular work. You have to set it first.
Sir, do you not agree about my given point regarding the parameter range about transfer mode?
But parameter range, say you are telling 180 to 250. This is a huge range. It may happen 180. It may happen also 250. So this is well known. If you increase the range, everything will come within that range only.
Then what at
Can
what
you tell
current
the
and
parameter?
voltage?
Say, can you specifically say that it happens exactly 150 to 160 like that small range? It's very difficult to say like that.
Yes, yes.
That is my point. Is that is the thing. So everything more
So
of within that range, everything will come out. Yeah.
So we can't we can't give the opinion about current range and voltage range to decide the transfer mode.
No, it's very difficult until unless you are not seeing, you cannot doing the your experiment of your own. We cannot say like that.
Sir,
Like
can you give
can't give
a suggestion regarding how to do trials about to check the transfer mode? Which type of instrument or trials which are using?
you have the welding machines. You have the welding machines. You do the trials by changing the current, different current values, mainly the current. Okay, change the different current values, keeping voltage automatically will be adjusted, and save the other parameters, the optimum parameter. That means that secondary parameters, say sealing gas flow rate and gap and all these things. Other secondary parameters set it. Surface preparation should be good enough, so that will good surface finish. Then you test it, that changing the different current, only change the different current. Then you can see that what are the different modes of the transfer occurs. Normally it is affected by the current only. Normally.
Okay.
By changing the current, you can change the mode, I think.
There will be an effect on the arc when changing the transfer mode.
What?
Is there an effect on the arc?
Effect of?
The, suppose there will be change in transfer mode, then the effect will be on the arc generation. Effect of transfer mode on effect on transfer. Suppose short circuit mode is transferred to change to global. Is there effect on arc.
Arc will be
Sir,
created
my
first to
question.
generate the arc, no?
Yes, yes. My question is,
Creation
suppose
of the arc, but not the arc, but it is should be affected by the arc length, the gap.
okay,
Significant parameter gap. Okay, gap is very low means you can expect the short circuit. Okay, very low
no, sir.
gap in short circuit. You have to maintain the standard gap.
No, sir. My question is, suppose while welding, suppose the transfer mode is changed from short circuit to globular mode. How effect on the arc?
Short circuit means very length, arc length is very low, and globular means arc length will be more than that standard values.
Okay.
And
Okay.
two
While
gap, then arc will not be sustained, able to sustain them.
okay, there will be effect on the arc, sir, while welding.
What arc effect?
Well pull.
Arc you are getting,
Arc.
you are generating the arc. Until unless you are not creating the arc, you will not be able to join welding.
Yes. Yes.
Okay.
There will be effect on arc generation. There will
Can
be
you give some hello?
Hello.
Can you give some idea about examination, how to prepare and what are the questions, and whether it will be online or offline?
It's already online examination, multiple choice type questions, and whatever pattern you are following the assignment, the similar kind of the will be in the exam.
Thank you. One more question is that, sir, in diffusion bonding, what is the depth of penetration we will get?
Depends upon the material surface preparation, but very low depth we can get.
Very low. And where the application actually?
Time also depends on time.
Yes, sir. Yes, sir. Yes, sir. What is the application area for diffusion bonding welding?
See, diffusion bonding is very old process. Earlier, very precision, and where is the very aerospace engineering also. They try to even till now they are following the diffusion bonding process or diffusion welding process. Till that is called as a reliable process. But thing is that here the main thing is that surface preparation. It depends successfully. It depends on the surface, how we are preparing the surface. Okay. Contamination, small amount of the contamination will not help the diffusion bonding. Okay. So in that case, very without any contaminated layer, you can to join intimate contact. Even sometimes we add the temperature, raise the temperature, keep on holding for a long time, and we can contact this diffusion bonding process.
Sir, one doubt was there. Okay, time is over, sir.
Yes, I'm running out of time now. Please. Yeah.
Just sir, 1 minute. In EBW welding, electron beam welding, there was some parameters recoiling pressure or recoiling force. So can you please elaborate, because it was not clear. Recoiling.
Recoiling. I think recoiling pressure that is not the input parameter. Okay. So recoiling pressure, I think when you're performing this thing, recoiling pressure is basically associated when you're creating some kind of the vapor domain has been created, which even we can find out in the laser also. Okay. Yes, so vapor domain, keyhole. When there is a generation of the keyhole, there the recoil pressure comes into the picture. And the recoil pressure is basically a keyhole means the dynamic balance, basically the molten metal and the vapor, because some vapor domain will be created. So dynamic balance between the vapor domain and the molten material. Okay. And recoil pressure will try to keep it opening this keyhole up to this. And when keyhole moving all this thing, making a balance, dynamic balance between the depth of penetration and the liquid domain and the solid liquid domain and the vapor domain, making the dynamic pressure, and that keep it opening because of the recoil pressure. Keep it opening this particular key.
So basic doubt comes from here that yes, sir. Basic doubt comes like vapor is very light in weight, density wise. So vapor should always go out of the material, but however it is going inside the material.
That's why pressure is required, no, to keep on this thing. So vapor domain has to be created, has to be sustained in keyhole. So how we can sustain? Only it is a very high pressure has been created to make this vapor domain up to the depth of penetration, up to the size of the keyhole.
So
That
this
has
pressure
to be
is being
that's the
created by molten
evaporation
pool or molten pool or
molten
electron
pool.
beam. Molten pool.
Yes, it is in the
Pressure
molten pool.
Yes,
Within
the pressure
molten
is
pool.
being created. Pressure is being created by molten pool.
Yes.
Okay. Okay. Thank you, sir. Thank you. This was the doubt. Anything also you can suggest about EBW? Because our
Anything?
domain is to work in EBW. Using EBW, we are making superconducting cavities. So you can suggest some more, put some more light on EBW process and welding.
Yeah. But electron beam welding process, even I think you have the machines. Do you have the machines?
Yes, we have machines. I'm from atomic energy, so
Okay,
we are
I
working for
understand.
superconducting LINAC.
Okay.
And we are welding niobium material, high purity, very high purity niobium material, which will be used at 2 Kelvin temperature.
Okay.
So we have qualified also. We have welded, we have qualified. Sometimes we get puncture. So that phenomena we are not able to justify how it is getting puncture. Only some hole occurs while welding some two cavities or two half cells, you can say, on the equator, full length will be welded. At some location, it will puncture. So anyway, we repair also. But why it happens, don't know. After the
Then we can discuss the problem also in detail.
Only 4 mm.
That's very high thickness. 34 mm is very huge thickness.
And
so anyway, this can be discussed in different front maybe. Okay. So you can explain. We can directly interact with me also. No problem. You can send me.
Sure, sir. Definitely, I would like to talk to you.
I have to look basically. I have to see that what is exactly happening.
Sure, sir. Please. I will keep on interacting. No problems.
Yes.
Thank you very much, sir. I am basically in Raja Ramanna Center for Advanced Technology, Indore. I had spoken you once by phone also. Thank you very much for your suggestions, and I will keep on interacting. It was nice to talk to you. Bye.
Hello. Hello, Swarup sir.
Hello. So I think we have this thing. I'm about to leave now, please. So it is. I have another meeting actually now from 5. So
Okay,
so
okay,
1 hour. No, we are supposed to 1 hour. Maybe if you interact with through email or other way, you can interact or maybe net. Right?
Okay, sir.
Yeah.
Okay, thank you.
Okay, thank you very much for your time also to interact with me. Okay, thank you.